This is the first lesson in our first unit of analytic geometry, and we're moving into looking at dilations and how that fits into similarity, and then also other transformations and how that relates to congruency, mainly with triangles. So today we're going to investigate the properties of parallelism and the center. And you have slotted notes, so if you'll go through and fill those in as we go. Think about a window on your computer screen. You know that when you click on it, you have the option of where you would like to drag. But notice that when I stretch it horizontally or vertically only, it gets distorted. In order for it to not get distorted, I have to grab it by the corner and drag it, and then both the horizontal and the vertical change at the same time and at the same rate. So right here, this type of transformation or motion is a non-rigid motion, because we've talked about other transformations such as translations, moving something right or left, up or down. We've talked about reflections, flipping it over the x-axis or the y-axis or the origin, or about a certain line, horizontal or vertical line. And then we've also talked about rotations. All of those are rigid motions because they don't change the shape or size, but dilations would be considered non-rigid because they do change the size of the figure. Alright, so right here we have non-rigid motions. We just talked about this. Non-rigid motions are transformations that change the figure's shape and or size, mostly the size. These are in contrast to rigid motions, which I just mentioned, that would change or would maintain that shape and size. So those ones that we looked at back in Unit 5 are translations, rotations, and reflections. Specifically, we're going to look at dilations. And dilations are transformations in which a figure is either enlarged or reduced by a scale factor in relation to a center point. And we'll talk more about the scale factor in a minute. Alright, so some key concepts. Dilations require a center of dilation as well as a scale factor. I need both of those things in order to do a dilation. The center of dilation is the point about which all points are reduced or enlarged. And the scale factor is something that I'm going to multiply each of the lengths of the sides in order to either reduce or enlarge the figure. In order to find the scale factor, you're going to use the ratio of corresponding sides. So if I've given you a figure and you want to know, or you're trying to determine the scale factor, you're going to have the length of the image side over the length of the pre-image. Remember that the pre-image is your original image. The image is your new image once it has been transformed, and in this case dilated. So notice that the scale factor takes a point P, so here's my P, and it moves it in a line in relation to the center. So that now I take my scale factor, and the length of CP is now the length of whatever K is, my scale factor, times CP. So in this case, it's enlarged it, or it's made it larger. If a scale factor is greater than 1, so if I take all the lengths of the sides and I multiply them by 2, that figure is going to be stretched, or one word that we use to call to name that is an enlargement. If it's between 0 and 1, so let's say I multiply every side length by a half, then the figure is compressed or made smaller, and another word for that is a reduction. If the scale factor is equal to 1, then this is called a congruency transformation, because if I multiply every side length by 1, it doesn't change it at all. A couple of things to note. Angle measures are always preserved in dilations. Orientation is preserved, meaning if I have a triangle ABC and it becomes dilated, so let's say I reduce it, A prime, B prime, C prime, orientation means that the letters are still in the same order. Remember, if I rotate a figure or if I reflect a figure, that's not the case, but it is true for dilations as well as translations that the orientation is preserved. This will become a little bit more clear when we see an image in just a moment, but the sides of the pre-image are parallel to the corresponding sides of the image, but notice that BC is parallel to B prime, C prime. Alright, when we talk about corresponding sides, they lie in the same position, so BC and B prime, C prime are corresponding sides. They represent the same thing, but in different figures. And then our notation for dilation, D for dilation, K is my scale factor. So if I take a coordinate x, y, and I apply that dilation, it becomes K times x, or my scale factor times the x coordinate, and the scale factor times my y coordinate. The center of dilation is typically the origin. Not always, but typically, and most of the things that we're going to look at are a center of dilation of 0, 0. Again, you can read through this, but we have a figure in just a moment that will explain it a little bit better. The corresponding points in the pre-image and the image are collinear points, meaning that they lie on the same line with the center of dilation. So when I look at this figure, here's my original pre-image, VTU, and then here's V prime, T prime, U prime. So notice that V and V prime are collinear. From my center of dilation, they're collinear. They lie on that same line. So that's what that last statement was expressing. Some properties to remember, and then some common errors. So let's look at a couple of examples. It gives me this figure, and it asks me if this is a dilation, and to justify my answers using the properties. So when I look at this, notice D moves from D to D prime. Everything gets multiplied by 2. E to E prime, again, multiplied by 2, and F to F prime, multiplied by 2. So the scale factor is consistent. Notice also that my angle measures are preserved. That's what these tick marks mean, that the angle measures are preserved. And notice that the orientation is preserved, so the letters are in the same order. So we have the shape and orientation of angle measures all been preserved, and then notice we have a scale factor of 2. This is asking me, so yes, let's go back. Yes, that would be a dilation because it holds all of those properties hold true. The following transformation, is it a dilation? And then justify my answer. So I've got TUV, TUV, looks like a G, I'm not really sure, but we've got this rectangle here. And then notice we have the one that's prime here. So it asks us if it is a dilation. Well, notice if you think about that window that I had at the very beginning where I clicked on it and dragged it, if I were to click on this, this would only be changing horizontally. It's not changing vertically. So I didn't grab it by the corner and change the whole thing horizontally and vertically at the same rate. So even without doing anything, I can tell you that that's not going to be the case because I have reduced it horizontally, but I have not reduced it at all vertically. So, so notice that the vertical corresponding sides have a scale factor that is not consistent with the scale factor of the horizontal sides. So my horizontal sides, the scale factor would be 2/3 because it's been reduced by 2/3, but my vertical, it would be a scale factor of 1 because it has not changed at all. So that would not be a dilation. And lastly, it tells me that this transformation represents a dilation, and it asks me what is the scale factor, and is this an enlargement, a reduction, or a congruency transformation. So notice my vertices A, B, C, that's my pre-image, and the side lengths, the corresponding side lengths. So 12 goes to 3, 10 goes to 2.5, and 15 goes to 3.75. Notice I'm taking each of those sides and I'm dividing them by 4, which means my scale factor is 1/4. And it is consistent among the sides. So this does represent a dilation. My scale factor is is 1/4, and this would be a reduction.